My name is John,
And I'm Adam.
and today we're presenting a paper on a supercapacitor-based energy storage system for elevators with soft commutated interface. For the presentation layout, we'll go over the why, the how, and the findings.
For the why, we're looking at the uses of supercapacitors. Supercapacitors are energy storage units that are the modern day way to store large amounts of energy in very small spaces relative to the older technology. So using supercapacitive storage tanks to transfer energy for a transportation system between point A and point B, it allows for very quick transfers of power that can move the system faster than standard or older practices. This study examined the supercapacitive systems application in the elevator system, as the current systems generate a lot of waste energy and heat and mechanical energy is lost, and they produce a very large power draw in the power grid. The study is done by looking at the power demand and power draw of an elevator system with and without the supercapacitive power banks in order to avoid unnecessary large power that could blow a circuit.
The study used experimental elevator simulations. They were run with a 720 kilogram car and a 1440 kilogram counterweight. The car was lifted and lowered 10 total floors, and the elevator speed, position, instantaneous power, and consumed energy were graphed.
So, looking at the power demand of the simulated system, we're looking at how sharply the power demand and power supply would spike as it goes along its path. So the trend of the electrical current as well as the power demand are very much the same because they go hand in hand. So as the elevator requires more power, there's more current that's put through the system to supply that power. The supercapacitive bank is theoretically best built using identical capacitors run in series so that they could run the most current through them. The issue is that if you have real life capacitors that are not exactly the same, then you create non-ideal issues. So the way that they countered that issue was using a power converter, and then they had to connect some of the capacitors in parallel. It lowers the overall efficiency of the grid.
And during the study, they found numerous problems, and they had to find solutions for. One of them was high power peaks that the power grid had to handle. And one of these ways they did it was use capacitors to reduce the system peaks, and the tank remained charged during the operation continuous power draw. For low efficiency of the direct coupled charging strategy, they used a power electronic converter to achieve close to unity with lower charging currents. For unequal load distribution across the cells, the active voltage sharing method was too expensive, and so they used parallel supercapacitors in series, which led to equalization. For low voltage in the supercapacitive tank, they used an electromagnetic transformer to produce high voltage side and a low voltage side to the system. And for low efficiency in the buck converter due to conduction losses, they used a zero voltage transition, or ZVT, and zero current switching, ZCS, to provide a possible solution. No stress caused on the DC side, so the losses were minimized.
For the findings, we found that the supply current with and without compensation shows significant smoothing of the power profile of the system, with the compensation being far smoother, as shown on the right-hand side. The solutions presented in the last slide compensate for high power fluctuations. It includes a bidirectional energy flow, good flexibility for sizing of the voltage load, and it also reduces the amount of components in the voltage-based circuit. The goal of having a higher unity of about closer to 1 meant that they were unable to use low power direct current, forcing the use of power electronic circuits in order to power the system.